Hello students, welcome back to Vassiversity. Right, today we're going to be working on hyperbolic functions. So, certain even and odd functions and combinations of exponentials, specifically e to the x and e to the negative x, are very frequent in mathematics, especially in calculus. So that we can even give them special names. Right, so some of the analogy of the trigonometric functions, we can have hyperbolic functions that essentially make hyperbolas on the regular Cartesian space. So let's take a look at some of the hyperbolic functions that we can define by observing the behavior of a combination of e to the x and e to the negative x. So we can have a hyperbolic sine, cosine, tangent, cosecant, secant, and cotangent, right? And it's a very similar definition as for the trigonometric functions, right? But trigonometric functions are related to circle, but this one's related to e to the x. So not quite the same graphs, but will be very similar approach of what we do for identities. So let's take a look at some of the graphs that those functions produce. So here is, for example, we have a figure 1, right? So it's a combination of 1/2 e to the x and negative 1/2 e to the negative x, right? Creates the y equal to sine, hyperbolic sine, right? We call it sinh. And then here is the cosh, or the hyperbolic cosine. So essentially a combination of positive 1/2 e to the negative x and positive 1/2 e to the x, right? Makes essentially this kind of hyperbola. And then for the hyperbolic tangent, this is going to be the function where we can see we have two asymptotes, right? And the asymptotes are plus. So if we approach infinity, x infinity, we are going to approach 1. If we approach negative infinity, we're going to approach negative 1. Okay? So note that the hyperbolic sine has a domain and range of all real numbers, while cosh has the domain from positive 1, right? So the domain, real numbers, but the range is from positive 1 to positive infinity, right? And the domain of the, obviously, tangent, right? Hyperbolic tangent is going to be all real numbers, but the range is going to be from negative 1 to 1, if we just consider regular tangent. Okay. So some of the applications that can be done in engineering and science occur all over those fields, such as in light, velocity, electricity. Right? Those functions appear a lot due to the fact that they are related to the exponential function, e to the x. E to the x is a very famous function. Later on, we will be learning about differential equations, and we will find out that differential equations relate to the exponential function, x. Okay? So one of the interesting things is, for example, the hyperbolic functions, right, appear in description of ocean waves, right, on the two-dimensional scale. So for example, this equation of the velocity of the waves, right, can describe essentially the profile, right, the profile of the idealized ocean wave, right, if we are looking at it from the side, not three-dimensional. Right, three-dimensional case would have more complicated equations. Okay, so, but for example, this equation can describe the behavior of the ocean waves, and sometimes in such approximation, we can model it. All right, so let's go ahead and take a look at some of the identities and prove some of the identities for the hyperbolic function. Okay, so here it is. We have hyperbolic identities, and that's going to be essentially hyperbolic sine, so it's an odd function, and cosh is going to be an even function. Then similarly, as we had for the trigonometric function, we can do similar identities. So hyperbolic cosine squared minus hyperbolic sine squared is equal to 1, right? And then from there, we can develop something like this. 1 minus tangent. Hyperbolic tangent squared is equal to secant. Hyperbolic secant squared. Okay? So let's go ahead and prove some of them. Right? So proof. Let's take a look. So let's go ahead and I'm going to call this one to be A. And of course, let's do this one to be B. Okay. So I'm going to prove A. So we have hyperbolic cosine of x minus hyperbolic sine of x squared. Okay. So that one's going to be equal to, so e to the x plus e to the negative x divided by 2 squared minus e to the x minus e to the negative x divided by 2 squared. Okay, so simplifying that and evaluating the square, so we're going to have e to the 2x plus 2 plus e to the negative 2x divided by 4 minus e to the 2x minus 2 plus e to the negative x divided by 4. So, combining those two fractions, we know that this and this cancels out. So, e to the negative 2x, e to the negative 2x. So we're going to be left with 4 over 4, which is equal to 1. So perfect. So the first identity proved. Now the second identity should be pretty straightforward to prove. Right? We're going to have, essentially, we're going to start with the first identity that we just proved. So hyperbolic cosine of x minus hyperbolic sine squared of x is equal to 1. So let's go ahead and multiply the entire equation. The entire equation by 1 over hyperbolic cosine of x. We know that it is non-zero, right? It does not cross 0, so we don't have any restrictions on the range of that function. So therefore, we can divide by that function. So if we distribute to every term, we're going to get 1 minus hyperbolic sine squared x over hyperbolic cosine squared x is equal to 1 over hyperbolic cosine squared x. Okay? And by using the definitions of the hyperbolic functions, we will end up with 1 minus hyperbolic tangent squared of x, which is equal to hyperbolic secant squared of x. Okay? Perfect. Perfect. So we can compare it essentially, right? We can compare it to the trigonometric function, right? So this is so for circular functions we would have very similar, but for hyperbolic functions we would have it slightly different. So if we would decide to parameterize, right, parameterize hyperbolas, we would end up with something like this, right? We can envision a hyperbolic function, right? So essentially we have the hyperbola, which is x squared minus y squared is equal to 1, and precisely we can parameterize it, right? If x is equal to the hyperbolic cosine, and y is hyperbolic sine. Okay, so now let's go ahead and learn about the derivatives. Right, since we're in calculus class, we also care about the derivatives, and we already know how to take the derivatives of exponentials. So the derivatives, essentially, of a hyperbolic function, since it's related to exponential, will be pretty easy to take, right? Because it's related to e to the power of x. But the formulas, right? So derivative of hyperbolic sine is cosine, hyperbolic cosine is sine, right? So signs here don't change. Hyperbolic tangent is going to be secant squared. Then essentially the cosine, so the secant and cosecant. So this one cosecant, this is a secant, and this is a cotangent, right? So we will be able to use that. So here one of the examples, right, we can also use the chain rule. So, for example, if we want to take the derivative ddx of hyperbolic cosine of square root of x, we would have to use chain rule. So that would be hyperbolic sine of square root of x times the derivative of square root of x, and that would be hyperbolic sine square root of x over 2 square root of x, right? So that would be the derivative, right? And we can do the same thing by using those rules and by using the rules, the power rules and chain rules and the quotient rules. We'll be able to take the derivatives as we wish. Okay, now, of course, those kind of functions also have the inverse function, right? So now let's take a look at inverse. So inverse of hyperbolic functions. Okay, so the inverse would look like this, right? So if we have essentially now we have the hyperbolic function of y is equal to x, so we would have a hyperbolic function of x. Okay, and so the important part is for us to be able to sketch it. So some of it not going to be immediately obvious, right? So for example, sinh itself doesn't look too much different to what a regular sinh looks like. So, but here is a example, right, of the graph. So here is the hyperbolic inverse sine, hyperbolic inverse cosine, right? Cosine, that would make sense, right? It does not exist on the negative side due to the fact that it actually will be related to the logarithms. And then here is the inverse hyperbolic tangent. Okay, so but the actual functions, right? The actual functions is as following. So, and we're going to prove one of it, and the rest are going to be an exercise for you to try how it's done. But essentially, the actual algebraic functions in its closed form are as following, right? Hyperbolic sine is going to be natural logarithm of x plus square root of x squared plus 1, where x belongs to the real axis. Or cosine, hyperbolic cosine is going to be very similar, but with the negative sign, and x is going to be greater or equal to 1. And the reason why is because to make sure that well, first of all, the square root cannot be negative, right? And the logarithm also cannot be negative. So we'll have to for both. And the square root will dictate the actual range here, the domain. So, okay, perfect. So now let's go ahead and prove number 3. Okay, so proof for 3, right, specifically. So we will have that, well, let y to be inverse hyperbolic sine of x, right? Then what are we going to have? We're going to have that x is equal to hyperbolic sine of y, which is equal to e to the y minus e negative y over 2. So rearranging it, we get e to the y minus 2x minus e to the negative y is equal to 0. Well, now let's go ahead and multiply the entire equation by e to the y. Right, e to the y can never be 0 because it's an exponential. So therefore, we will get e to the 2y minus 2x e to the y minus 1 is equal to 0. So we can notice, right? We can notice that we can write e to the y squared minus 2x times e to the y minus 1, which is equal to 0. So that is a quadratic equation, right? And the way we can see it is if we say, well, let e to the y to be equal to t, then what happens? We're going to have t squared minus 2x t minus 1, which is equal to 0. Okay. And therefore, solving for t, right? So t, which is equal to e to the y by the quadratic equation, we will have 2x plus or minus square root of 4x squared plus 4 divided by 2, which is equal to, so simplifying it, it's going to be x plus or minus square root of x squared plus 1. Okay. So the key thing here is to notice. So note that e to the y is greater than 0, but x minus square root of x squared plus 1 is going to be less than 0. Why? Well, simply because x is going to be always less than square root of x squared plus 1. Okay? Thus, the negative solution is not a solution here. The negative sign solution is not a solution here, a valid solution. So we're going to have e to the y is actually equal to simply x plus square root of x squared plus 1. Now applying the natural logarithm to both sides of the equation, and we will have y is equal to natural logarithm of x plus square root of x squared plus 1. And we remember that y was equal to inverse sine. So inverse sine of x is equal to natural logarithm of x plus square root of x squared plus 1. Okay. So now try to do the same thing for number 4 and number 5 to prove it that it's actually the formulas that we showed are actually true. Okay. And then the last part is the derivatives, right, of the hyperbolic functions. So this is also part. So let's add and take. So derivatives of inverse hyperbolic functions, right? Similar to what we would have for the inverse of the trigonometric function. Slightly different. Slight difference, of course, right? But let's go ahead and prove the first one, right? The very first one. So proof. So we will say e dx of sine, hyperbolic sine, inverse hyperbolic sine of x is 1 over square root of 1 plus x squared. Okay, so how are we going to do that? We're going to say, well, let y to be the inverse hyperbolic sine of x. Okay, then, right from that we know that x is equal to hyperbolic sine of y. Then we can differentiate this equation implicitly, right, essentially by using what we did for the related rates. Right, if we take a derivative with respect to x, and we know that y is dependent on x, so we will have simply 1 is equal to hyperbolic cosine of y times dy dx, which is equal to 1. Okay, then since we remember one of the identities, right? The hyperbolic identity, which is hyperbolic cosine squared of y minus hyperbolic sine squared of y is equal to 1. Then, for hyperbolic cosine of y to be greater or equal to 0, right, what do we have? we will have the following, that the hyperbolic cosine of y is going to be positive square root of 1 plus hyperbolic sine squared of y. Okay, so therefore we can plug in into the expression, right, into this expression. So we know that dy over dx is going to be 1 over hyperbolic cosine of y, which is equal to 1 over hyperbolic, so 1 plus hyperbolic sine squared of y, and we remember what y is equal to. The inverse, right? Y is the inverse hyperbolic sine of x. So hyperbolic sine of an inverse is going to be just x. So that will end up being 1 over root of 1 plus x. Right. Perfect. And essentially, I will leave the rest for you guys to try out. So, perfect. That's essentially would be it for today's lesson. And in our next lesson, we will start learning about maximum and minimum values of the function by using the derivatives. Thank you.